Hello, Geo here. This is my first YouTube video, so please be patient with me. I think the subject matter you'll find interesting, but the presentation may be just a little bit rough because this is the first time I'm trying this. But we're in a brand new age, and I guess the world is changing. So people like me, why shouldn't we speak up? And I think I do have some interesting things to say. So my topic today is the theory of relativity, and personally, I trained many years ago as a geophysicist, so I know a little bit about physics, and I've always been interested in physics. And after I'd gotten my degree and so on, was out in the work world, I started pursuing my interest in the theory of relativity. I wanted to learn about it. I'd heard so much about it. I just wanted to learn what it was about, where it came from, and so on. I wanted to learn as much as I could about it, and so I have. And I can say that I know a fair bit about it, and also a long time ago I reached the limits of what I was ever going to know about it. there's some parts of the theory of relativity that are so complex, I think unless you're extremely smart, they will be beyond, well, they're definitely beyond my comprehension. But anyway, I do know a fair bit about it, do have some questions about it. I am skeptical about it, and I've got some reasons for my skepticism. So that's what I'm going to work through here today. So I'm going to break this talk up into a few different parts. First of all, I'm going to talk about the evolution of electromagnetic theory, because that really was the precursor to the creation of the theory of relativity. Second, I'm going to talk about just how the special theory of relativity came about. And then I'm also going to talk about the general theory of relativity, which is quite different from the special theory, and which took Albert Einstein an additional 10 years to create. So he came up with the special theory in 1905, fairly simple and straightforward theory, and then followed it up with an almost incomprehensible general theory in 1915. So I'll talk about the evolution of both of those. And when I'm talking about the evolution of them, that's when I'm going to talk about why I'm skeptical about them. And then I'll talk about, that third part will be talking about the proofs, I guess, of the physical measurements and observations that have been made to, I guess, perhaps prove or maybe disprove the theory. Then I'll follow up just with some general observations about the theory itself and what I think we should do and how it's impacted kind of our collective psyche, because it really has, if there's anything in physics that's really impressed itself upon the greater community, it really is the theory of relativity, which is very interesting, and especially considering what the theory actually is. I think there's, well, I'll get to that later. So I believe that what the theory actually is, and the mythology that's kind of been built around it in our society, they're two, I'd say, fairly different things. So it's quite interesting how things kind of take on a life of their own in our world. So anyway, let's get going. So the first thing, electromagnetic theory. So I'm not going to get into a bunch of equations in detail. Electromagnetism is incredibly fascinating. It's an incredibly fascinating field, and the evolution of the theories and just the application of them has just had profound impacts on our world. I mean, you take your cell phone, you take this computer that I'm doing the video on, that you're watching the video on, all of these things, they're all based on electromagnetic theory. So the amount of technology that's been built up based on these theories, just amazing. And so if you look back into the history of the evolution of electromagnetic theory, that is really quite something, and it's full of heroes, full of giants, intellectual giants. Many different people contributed to that, and I'm not going to talk about them all. This is about relativity, it's not about that, but just to suffice it to say, I'll talk about a couple though. So there was a fellow named Michael Faraday who lived in the early 1800s in England. He was an amazing experimenter. He would create this experimental apparatus where he would take careful measurements of things like voltage and amperage, so flow of electricity, uh, magnetism, the interrelationship of the flow of electricity with magnetism and the changing magnetic fields, how they induced electric currents and so on. Just incredible work he's done. And actually, if you're interested, all of his, well, I don't know about all, but a lot of his original reports are available online. You can download PDFs, you can read them, and they're actually quite well done and quite readable as well. So anyway, so Faraday was a great giant in the development of electromagnetic theory. Now fast forward a few decades in the 1800s to a guy named, because one thing that Faraday didn't have was any training, mathematical training. He was not a trained mathematician at all, so he did a lot of experimenting and did a lot of reporting on his experiments, but he didn't create any real mathematical framework other than just basic interrelationships. He didn't create kind of a coherent mathematical framework around electromagnetism. That job was left largely to a fellow named James Clerk Maxwell, who did that kind of in the second half of the 1800s. So Maxwell was a trained mathematician. I forget which. Was he at Cambridge? He was at one of the English universities, and he developed a very coherent mathematical framework that you could that would mathematically describe electromagnetic effects. And then other people took Maxwell's work and boiled it down. There's a guy named Heaviside, Oliver Heaviside, who boiled it down and ultimately came up with 4 equations called the Maxwell's equations, which really have been used a lot and really do form the basis of a lot of the technology that we use today and we just take for granted today. So here we go, and I'm not going to get into a lot of detail. These equations, there's a lot that could be said about them. I know a bit about them. I wish I understood them even better. But for purposes of this, I'll just show you these equations. So here you go. Here's the Maxwell's equations, and the capital E is electrical field, capital B is magnetic field, and they just talk about the interrelationship of the electric field and changes in the electric field with the magnetic field and so on, and very fascinating stuff. Ultimately, I just want to focus on this bottom equation, which is known as Ampere's law. So you've got the gist of this cross here denotes what's called the right-hand rule. So basically what it says is that if you've got a current moving down a wire, you've got at right angles to that current, you're going to have a magnetic field. But it goes on to add there's another term here, 1 over c squared delta E over delta T. So you've got the magnetic field created by the the current going through, but then you've got an additional magnetic field created by a changing current. That's what the deltas stand for here. And then you've got this, and this is the interesting part here. You've got this 1 over c squared term in here, and c is a constant, and it's the constant that I guess it was ultimately concluded, I guess must have been experimentally, that constant is actually equal to the speed of light. And the reason that's important, and this is a very profound thing that Maxwell's equations resulted in, the reason that's important is because this ultimately is the equation that describes radio waves. So you've got radio waves, the reason they can propagate over long distances is because you basically got a magnetic field turning into an electrical field, which in turn turns into, it's just an induction back and forth between a magnetic field and an electrical field. It's just back and forth, back and forth, and back and forth, and it's moving through space. And that's why you have radio waves. I mean, that really describes radio waves. So the interesting thing is, if this constant c is equal to the speed of light, which I believe is 300 million meters per second, then the further conclusion you can come to is that that means that light is actually electromagnetic radiation, which is really, I guess, largely believed to be true. I believe it. So, and that in turn is very interesting because the electromagnetic spectrum covers a large range of frequencies, and the visual portion of that spectrum is just a sliver. It's minuscule relative to the overall. So you've got, FM radio, AM radio, shortwave radio, ultra high UHF radio, ultra low frequency, just a huge range of radio waves that are in around us. We don't see them, but they're there. But we do see some of them, but just a very small sliver of them. That's light, colors. And so I always say, well, if what we can see is only a small sliver, we always see, if only what we can see with our eyes is only a small sliver of the overall, electromagnetic spectrum, then if you generalize on that, then what we kind of experience as human beings, that's we probably got a whole huge world in front of us of all sorts of things that we just can't, we just are incapable of being aware of or whatever. Anyway, so that's just my thought. So, but back to the special theory of relativity. So you've got this conclusion that, oh, geez, light is just radio waves. Okay, fair enough. Then you have this big debate. This is in the late 1800s, involving this Lorentz transform. So you see that Maxwell's equations show C to be a constant. So then Lorentz had this notion, I guess. I guess physicists generally at the time had this idea that if for any sort of physics theory to be correct, it had to work. It had to be congruent in all inertial frames. So it had to work the same. If you're sitting still, and motion is relative, but anyway, if you're sitting, let's be, it's all about us. So if I'm sitting still, and there's some guy that's going by in a train, and we're both observing the same physical phenomenon, we ought to be able to come to the same conclusions about that. Me applying physical rules in my inertial frame, meaning sitting still. So I'm it's all about me. I'm sitting still, and I'm going to apply the rules. And then the guy on the train says, no, it's all about me. I'm moving on this train, so I'm going to take the same rules. I'm going to apply them. I'm going to get the same result as you. It doesn't matter, Geo. Say all the same. Okay, so that was the idea, and that didn't work with Maxwell's equations, because Maxwell's equations yielded the result that the speed of light is a constant, and the speed of light, I guess, is a constant in all inertial frames. So if I'm standing beside the railroad tracks and a train comes by and there's a flash of light, as the train's coming towards me, there's a light flash coming from the train, from the light bulb on the train, then that flash of light's coming at me at the speed of light, c, in my inertial frame. There's no velocity added to the speed of the light because of the speed of the train. And this is different from, say, sound waves, and it's also different from, say, just physical objects. So, for example, that same train, you've got the light bulb flashing, and right beside it, you've got a pitching machine, say. And the light bulb flashes, and at the same instant, a pitching machine pitches out a baseball. The baseball actually, let's say the train's going 50 miles an hour, and the pitching machine pitches the baseball out at 100 miles an hour, say. Well, in order to, from my perspective, in order to determine how fast the baseball is coming at me, I have to take the speed of the baseball source plus the speed of the baseball, that the speed that it comes out of its source at. So 100 miles per hour it comes out of its source at, but the source itself, the pitching machine is coming at me at 50, so that's 150. And then you'd say, well, shouldn't it be the same for the speed of light? And shouldn't it be like if it comes out of the light bulb at the speed of c, but then you have to add the 50 miles, so c plus 50 miles per hour. You'd think that would be the logical response. But for whatever reason, these guys that were debating this back in the 1800s said no. Now, if it was a sound wave, if it was a horn, then they would say, yeah, picks up that extra velocity. It's the speed of sound plus 50 miles per hour, and that's why you have the what's that effect called? Where trains come, the train whistle as it's coming towards you is higher pitched, and then as soon as it passes you, it goes to lower pitched. Well, that's what that is. It's the Doppler effect. So that works. But they say, oh no, it doesn't work for light. Okay, so this caused a big problem. There's a big debate over it. And he had this Lorentz transform, which he said, like if I use this transform, we can apply these Maxwell's equations in any inertial frame. If I'm on the train, I'm off the train, doesn't matter. We'll get the same results. We just have to do these transforms and correct for it. But they don't work because the speed of light doesn't budge, and it doesn't change. And so that was a big problem and a big debate, and nobody could solve it. And then along comes Albert Einstein, and Einstein says, oh no, he says, this is not a problem. This is just the way it is. Like the speed of light is constant, so something else has to give. So time isn't constant. So if the light source is on the train and you're standing still on the side of the tracks and it's coming by you, and it's still the light's moving at the speed of light, but time for you on the side of the tracks is I guess compressed. I think goes slower or goes fast. I don't know, one or the other. So it's time that gives. So this was the whole. This opened up the whole, I guess, world or can of worms or Pandora's box or whatever you want to call it, of extra dimensions and time, is not a constant and all this stuff. Okay, so there you go, Brave New World, and it really did create a brave new world, because all of a sudden we're all looking at things differently, and it looks like there was quite a stir over that theory that Einstein came up with. Okay, fair enough. But I guess what I'd say is, if light is moving at the speed of 300 million meters per second, that's pretty fast. And I suspect that those guys at that time, well, I'm pretty sure those guys would have had no way. Well, actually, they did do an experiment where they had mirrors at right angles, and they wanted to see if there was this so-called ether, and that the light would move through the ether just like sound moves through the air. There's a physical medium that carries sound. And there was a theory that there was ether, the physical medium that you just couldn't see or couldn't experience or whatever, that carried light. And so they've done this experiment and said, no, there's no ether, so light is different. And I think that might have been part of why they said that light couldn't pick up extra speed from its source and so on, that there was basically a universal speed limit for light equal to c. So anyway, that's what they came up with. But again, that's one of my first challenges is I'm not so sure about that. I think that the speed that everything would be measured at would be so small relative to the speed of light that in fact you wouldn't actually really be able to conclude physically that the speed of light did or did not pick up, I guess, momentum or pick up extra speed from from the speed of its source. So I would say that they would have been better off saying, no, you know what, that speed of light is not a constant. You know, in a motionless light source will emit light at that speed, but then you have to add or subtract the speed of the source relative to you. And I think that, you know, for most intents and purposes, you would have been able to just say that was a negligible amount and therefore we're just going to ignore it, which is done all the time in science and in particular in engineering. Yeah, so I think they kind of missed the boat on that one, and where it's taken us is fascinating. But I'll just say one more thing about the special relativity. So basically, you've got this contraction of time. Something's got to give. Like if the speed of light can't change, something's got to give. And for Einstein, it was time. So all this in time could expand, contract, and so on. But then if you took this to the extremes, and I'll just give you the paradox of the twins. So you got two guys, two identical twins, and one of them hops on a spaceship and off he goes at some speed near the speed of light, right? So he's moving very, very fast, so all of a sudden you can't say the speed of light is negligible. And then, you know, 20 years, you know, he's got this clock, calendar, whatever. He's got some sort of clock that tells him what time it is. He's not by the Earth, whatever. 20 years go by, he goes way out, comes way back, and only to find that his brother has been dead for several hundred years. So for him, time slowed down because he was moving so fast. And for his brother, time didn't slow down. Okay, but then what happens if, say, both he and his brother got on that same spaceship and took off, but then his brother gets on another spaceship that takes off heading, you know, immediately heading back to Earth, such that the brother who took the second spaceship is just sitting right beside Earth for 20 of his years, and then at some point that brother turns around and goes and catches up with his brother again, and then he finds out, the brother that was at Earth finds out that his brother's been dead for 200 years or whatever. So basically the motion relative to one another is the same in both cases, I think. And yet one guy gets old quicker, but if you look at it the other way, the other guy gets old quicker, because motion is just relative. Like motion, I can say I'm the one standing still, but that's just a relative phrase. If you're coming by on a train, you can say, no, George, I'm Geo. You say, no, I'm the one standing still. You're zooming by 50 miles an hour or whatever. So to me, this paradox of the twins, I mean, when I learned about that, I read a little book about theory of relativity, special relativity. I thought, well, that's just crazy. And I still think it's crazy. And so that's pretty much it. The whole notion of expanding time or time travel and all these things, you know, captured the collective imagination of humanity. Well, that's fine, but I guess I just don't buy it. I just don't buy it. I think probably way back we should have said, no, you know, this C is variable. You know, it'll depend. Like the congruence across inertial frames will just require that that's not a constant. That there's going to have to be a correction for the actual speed of the source. Okay, but it is what it is, and I'm making this video just to challenge people's thoughts and maybe just expand on our conversation. One other thing that came out, I guess, when we humans started to put satellites out around the Earth, and I think even before that, I believe there was an experiment with a cesium clock, where they put a cesium clock on a jet plane, and then they flew that jet plane around and around the Earth, and they determined that the cesium clock had run slower. So this is some sort of a atomic clock, it runs slower. And so they said, well, that was because that's relativistic effects. And then when they started putting satellites up, apparently they had similar issues where they had atomic clocks on the satellites, and they ran too slow, and so they had to scratch their heads about it. Why are these, we just used Newtonian physics and so on. And ultimately somebody said, well, that's relativity. There's time contraction going on there. You have to correct for it. And so they applied, I think, the general theory of relativity, all the equations and so on, the tensor math and so on, and did these corrections. Well, I guess I'd say, okay, fair enough. I mean, maybe that's right. I mean, maybe relativity is real, and that's just the end of the story. You just have to correct for it, and the math is all right. But I guess I also think we should not necessarily take that as the final answer, and we should think about things, and we should start with the simplest possible conclusions, which is, and for me, that would be, look at the clock. You've got an atomic clock, which presumably, I don't know exactly how they work, but I believe it's by vibrations, or measuring the number of vibrations in the nucleus or something like that. Well, or decay, or I don't know what, but whatever that physical phenomena, atomic phenomenon is that is being used to provide a very precise measurement of time. If you think about it, you're further out. The gravity of the Earth, is what it is at the Earth's surface. You put a satellite up into space, and gravity is much, much less because you're that much further away from the Earth. So is it possible that the actual mechanical workings of these clocks is impacted by a different gravity environment? Just a thought. I mean, I just think that there could be other explanations in these. And the other thing is, I went to the Wikipedia page on these satellite corrections and so on, and it's a pretty complex, I guess, engineering problem, tracking satellites and so on. There's a lot of different things that have to be corrected for, and they're all pretty small. So again, I think that there's probably a lot of different ways you could look at that problem and explain it in different ways. And so anyway, I think as humans we should, because we might learn something. We shouldn't necessarily take the theory of relativity at face value. And then here's another thought about relativity. The redshift of planets. And again, I'm not an astrophysicist, but I've read about redshift, and this is interesting. Einstein, when he developed his general theory of relativity, he included what was it called? It was a universal constant, I think he called it. And he had to insert that because I guess the prevailing belief at the time was that the universe was static, and Einstein's equations actually resulted in conclusions that the universe was expanding, and so he put this constant in so that he could keep the universe static, and his equations would still work. And then later it was concluded that in fact the universe is expanding, and then Einstein said, well, I'm sorry that I did that, because it looks like I was right in the beginning without adding this constant. And then the reason, I think one of the big reasons why it was concluded that the universe is expanding is because when lights come back from stars, when you look at the light you look at the spectrum, the frequency of the light that's coming back, relative to, I guess, what it's believed the actual source frequencies are for the light. There's something called a redshift, and red is lower frequency than, say, all the other colors. So the gist of it is that, hey, these stars are moving away from us, and therefore the light, just like the Doppler effect, when a train moves away from you, the sound of its whistle is a lower frequency, Well, the same thing with these stars. They're moving away from us, therefore the light coming from them is a lower frequency. And again, so that's another question I have. So if the Doppler effect is based on sound waves moving through the medium of the air, and so you have to take into account, the motion of the sound source relative to you, and it's really all more just, I guess, Newtonian physics that's at play there. Then, if you have redshift of starlight, isn't that basically the same thing? And doesn't that again indicate that in fact the speed of that light is equal to c minus the speed that the star is moving away from us, and that's why you've got the lower frequency? I mean, to me, it's pretty obvious, and it seems like we're just doing a bunch of intellectual dancing around it. It seems to me. I mean, it looks obvious to me, and yet we're not willing to acknowledge it because it seems to go against the theory of relativity. Seems like to me. Maybe I'm wrong. Anyway, I've talked about the special theory of relativity and the concerns I have with it. Now on to the general theory of relativity. So, special theory of relativity dealt with basically contraction or dilation of the time dimension, so time became a fourth dimension. And then Einstein takes it much further, and he delves into the realm of gravity. And so I'm going to show you something here. I'm going to show you the what we believed about gravity before the theory of relativity, which was Newton's law of gravity. So Newton had come up with a very straightforward law of gravity, and here it is. So there you go. F equal G, which is a gravitational constant, times m1, which is the mass of the first. So this is the attraction to two bodies. So the mass of the first body is m1, the mass of the second body is m2, and then over r squared. So if you take our experience on Earth, so there's the Earth, and there's a guy standing on the Earth, and there's r, the radius, because if you do the math on this, that there's a certain average radius of the mass of the Earth. If you take the overall mass of the Earth, divide by the average radius and multiply by, and you'll end up with basically 9.81 meters per second squared for all, and then you multiply, and that's the acceleration, and then if you multiply by the mass of the little guy here, that'll give you the force. So that, and then, like I was saying before, you've got a satellite, and of course the r is a much larger number, which means the force is a much smaller number, and that's what I was talking about before. You have a satellite way out here, it'll have much less gravity, and therefore perhaps the atomic clocks are working differently just because of something about atomic clocks and gravity. Anyway, that was the Newtonian theory of gravity, and it worked quite well for a lot of things. Still does, actually. For the most part, that is the Newtonian gravity is what is used. I trained as a geophysicist, so I can tell you that I never saw any relativistic corrections done for gravity surveys. So, if you're looking for, metal deposits in the Earth, and you'll have very fine instruments that do very fine measurements of gravity variations on your surface, because if you have something really dense under the Earth's surface in a certain area, gravity in that area will be just slightly, very slightly greater than it is in the surrounding area, and you can actually map it. So that's a tool that geophysicists use. Geophysicists never, in my experience, would apply any sort of relativistic corrections on any measurements they were making. Now, one thing I am not is a geomatics expert. So you've got satellites moving around the world. They're forever defining and correcting what they call the geoid, which is just the picture of the Earth, the shape of the Earth, the gravity realm of the Earth, that sort of thing. I don't know whether there's any sort of relativistic corrections for those geoid type measurements. I'd be very surprised if there was. So anyway, Einstein spends 10 years developing this general theory of relativity, and the notion there is that gravity is not the attraction, should not be viewed as the attraction of massive objects. Instead, it should be viewed as massive objects impacting space-time. So suddenly we've moved from three-dimensional space, which we can all imagine. All right, we're able to appreciate, understand three-dimensional. We move to four-dimensional space-time. Time becomes just another dimension, which can be manipulated, which is manipulated by mass. And then the example that's always given is a stretched, so analogy is a stretched rubber sheet, and you stick a bowling ball on it, and everything, rolls towards the ball. You put a marble over here, and bowling ball's in the middle, and the marble rolls towards the bowling ball, and that's the way gravity should be viewed. And then Einstein comes up with these incomprehensible equations, tensor mathematics or whatever, which applies this. And then I guess that's what these different physicists have used, and they've come up with black holes and all this stuff. Okay, fair enough. But again, I guess what I'd say about it is Einstein started from a starting point of space-time and bending of space-time, mass bending space-time. And then he built extremely complex mathematics around those notions. I think that another approach that probably would have been equally valid, if not better, would have been to take Newton's basic law of gravity and then to add boundary conditions to it. So to say that, there could be situations where, generally speaking, Newton's law of gravity works. It describes planetary motion. It describes phenomena, gravity on Earth. It works. But there could be situations where, you've got extremes. Maybe you've got an extremely massive object and a very tiny object beside it, or whatever. So that maybe there's corrections to Newton's theory that need to be applied in certain situations, but for the most part, it is a law that works well. I think that you could have just said that you didn't have to monkey around with time dilation and so on and contraction. You could have continued to have 3 dimensions of space, which we can all visualize. Time could have continued to be at time, which was the same for all things, constant across all inertial planes or frames and so on. You could have done that, and probably you could have done it quite well, but we didn't. Well, I guess maybe we did, maybe we didn't, I don't know. So anyway, that's my other issue. Having said that, let me just move on to a couple of other things that have been cited as evidence of the existence of the theory of general relativity. So one of them was in 1919, where Lord Eddington, I believe, went to someplace, I believe in Africa, where there was a total eclipse of the sun. And so the theory, there was a star behind the sun. Or I guess at the time of the eclipse, the star would be behind the sun. And so astronomers knew where that star was in the night sky or whatever, but of course when it went behind the sun, you could never see it because the sun was, it was obliterated by the sun. But then you're going to have an eclipse of the sun, and so there was a theory that if the sun is so massive, well, the general theory of relativity, apply that, the sun is so massive so that the light will be bent around the sun, so it will actually move this star over effectively, because the light beam coming from that star will have been bent by the sun, and you'll finally be able to see it because the sun will be eclipsed. So he went and he did that, and hooray, and to much fanfare. hey, the general theory of relativity is real. We've proven it. The light waves bent and so on. And I guess what I'd say to that is, well, yeah, but wouldn't that also have happened if you applied Newton's theory of relativity? And then people might say, and I don't know the exact numbers. I know there were, it wasn't an exact fit, but I can't speak to the error bars and so on. But people say, well, yeah, but it wouldn't have bent that much or whatever. Maybe the photons don't have mass, so therefore, the m2 would have been 0, so that Newton's theory doesn't work. Well, photons may or may not have mass. I don't think that's established. And maybe even if Newton's law didn't work perfectly for that specific case, maybe that would have been one of those boundary conditions where we'd say, okay, Newton's law generally works, but it didn't work there. It's off by so much. And I'm not even saying it didn't work. Like, I don't know. Maybe it did work. But if it didn't work, you could say, well, it was off by that much, but, this was a very unique situation. You got a massive object there, and you've got this little tiny light wave, or light or photon or whatever a light is going through there, and there was something else that happened. It doesn't necessarily mean that there was a dilation of time or, a warping of time-space or whatever. It's something we can't picture. It could have been some nuclear effect or something. So to me, I'm not saying that Eddington's conclusion was wrong. I'm just saying I think there's other conclusion or other explanations that should be explored. Okay, so that's Eddington, and then there was one more thing about the progression of the perihelion of Mercury. So Newton's theory of gravity had done a very good job of describing planetary motion in our solar system, but there were a few glitches. There was one glitch in particular. It was Mercury. So Mercury has this perihelion. It's got a bit of some sort of a wobble or inconsistency in its orbit around the sun, and I guess the inconsistency was such that when you applied Newtonian physics to it, it didn't properly describe the actual motion. So there was a disconnect between Newtonian physics and the actual motion of Mercury there. Of course, the planet Mercury is the closest one to the sun, so on and so on. So, but then I guess if you applied general relativity, problem solved. So that was viewed as another proof of the existence of general relativity. And I guess I would say to that, I would say the same thing I say about Eddington's experiment, which is fair enough. Maybe Einstein built that into his theory. I mean, his incomprehensible mathematics. I mean, you could build a lot of stuff into it. I mean, they're so complex that if you knew that inconsistency existed, you could actually build your theory around that and use it to describe whatever you want. But having said that, you could also build other complex theories around it that didn't involve warping of four-dimensional time-space. It could have been just, there's something going on there. Needs further review. Could be could be nuclear effects of some sort. You've got, maybe it's the strong force, the nuclear strong force acting between molecules on Mercury and this massive star that's beside, and the proximity is such that you've got things that, you've got forces that generally are local in their effect and negligible at greater distances, because this object is so massive and there is such close proximity that in fact it's causing other things to bleed in to what is otherwise still a valid theory of gravity. Okay, so there you go. So those are largely my issues with theories. Now, one last thing, and I meant to mention this earlier because this really came out of the special theory of relativity. So Einstein's 1905 theory, and that is the equation E equals mc squared. So probably the world's most famous equation, and an equation that I hear in the most interesting places. I was watching this fellow on YouTube the other day, and he says, the Great Awakening is occurring. There's a lot of things that we just know. We know E equals mc squared. We know that there is just massive energy available, and we know from that famous equation and so on. And I find that interesting. I also saw a fellow, an expert in nuclear physics on YouTube, and he was saying, again, he said, yeah, E equals mc. We've got these reactions, we've got these nuclear fission reactions that generate so much energy, and we know from E equals mc squared that the maximum amount of energy you can get from any mass is equal to mc squared. And I thought, what? Really? Because nuclear physics, I don't think, uses relativity theory at all, and it's a totally different field. And E equals mc squared, and I'm going to describe here, I'm not going to get into detail, but I am going to describe where that equation came from. And E equals mc squared, in my view, is fun with math. It's like a parlor trick where some mathematician sat down and worked it out based on theory of special relativity, and hey, said, look at this. look what pops out when I kind of fool around with the number with these equations a little bit. Not sure that E equals mc squared really is much more than that, but again, that's just me. So I'll just tell you why I believe that, and you can make up your own mind on it. So anyway, on that note, I pulled out my university physics text from first year university way back in the dark ages when I was in first year engineering, and turn to the chapter on relativity, and specifically the section on work and energy. And that's it. There's some equations in there and so on, and there's some, as I say, fun with math, which is pretty typical actually for that sort of textbook. It's not unusual what is done to derive the E equals mc squared equation. So kudos to those guys that actually did it. Maybe it was Einstein that did it, I'm not even sure. So nothing wrong with the theory or the logic that's applied to getting to that conclusion, but I just want to bring clarity to what has been done to get so to step back, Newtonian definition, Newtonian physics definition for energy, or they call it work, say it's all the same, is equal to change in momentum over time. Change in momentum over change in time. And so if you have say a baseball, and it's you throw it and it's it's got wind drag on it, so it's slowing down. So it's got a certain amount of energy, kinetic energy, coming out of your hand. But then as it moves along, it slows down, and it has less kinetic energy. So basically, and that is change in energy. That's kind of where these energy equations come from. And I actually wrote down, so kinetic energy, E equals half mass times velocity squared. So that's the derived Newtonian formula for kinetic energy. And then you've got potential energy. So you've got a ball up at a height, and then you've got the force of gravity pulling down on it, and so on. Then the potential energy is gravity times mass times height. So it's just playing around, and of course you need to use those equations when you have, say, a hydro dam. Well, how much energy you got there? Well, the penstocks are 100 feet high. The generators are at the bottom of the penstocks, and we've got so much water up there, so that equals so much energy. So these or spinning generators that generate electricity, and then you've got also electrical energy, which brings in electromagnetism and so on. So this math is done all the time. So what they did in my first year physics text, and this was many decades ago. I taught this text. They basically plug in this, so the time contraction or dilation that comes out of the Lorentz transform. They basically take Newtonian classical physics definitions of energy and they plug in this correction for time dilation. And out of that, they come up with this equation for this equation here, right here. E equals mc squared plus rho c squared. And they say that the rho c squared represents actual energy from motion. So they say that if you reduce that to zero, like if the body is standing still, well then you end up with E equals mc squared. So they basically taken all the classical definitions of energy, plugged in this time dilation correction from the Lorentz transform that came from special relativity, and came up with this. Again, I call it a fun with math result. They threw a bunch of stuff around, worked it around, which is what they do all the time. I mean, that's what they do. I mean, there's nothing wrong with it. But I guess I just question whether it's actually true. And it does, again, depend on C being constant in Maxwell's equations. When you boil it all down, if C in Maxwell's equations is not constant but is variable depending on the speed of the source of light, well then E equals mc squared. It's all, you pull on that thread and everything unravels. So does E actually equal mc squared? I think probably not. But I know other people can beg to differ. That's fine. You can believe what you want to believe. So that's kind of it. That's what I wanted to say about, theory of relativity and so on, the issues I have with it. One other thing is Einstein, I think he was 26 years old in 1905 when he was working at the Swiss Patent Office and developed the special theory. That really, he developed that and other theories in 1905, and he was a very smart man. Don't get me wrong. I think Einstein was a great thinker and a great man. That really kicked off his real, career as a highly respected physicist. He spent 10 years after 1905 developing the general theory of relativity, and that was 1915. And then he spent the rest of his life, because he was also involved in developing quantum theory, he spent the rest of his life trying to develop a unified theory of physics where he could marry relativity with quantum theory, and he never succeeded. And to this day, I don't think anybody succeeded. And I tend to believe that relativity, we just need to kind of nudge it aside now. We can still give it a nod and so on, but I think we should really start looking for other reasons why certain phenomena that seem to support relativity, why they exist. Maybe there's other equally valid explanations which would facilitate moving forward better with developing physics theories that actually work moving forward. Again, just maybe my opinion. I'm not an expert, but that's good. But here's another thing about relativity, and this is something that I think is equally interesting to just all the math and so on that I've talked, the logic that I've worked through, is just the impact that relativity had on humanity. So here we are, more than 100 years after this theory was put forward, and we grapple with the nature of reality. What is reality? And I think, things like consciousness, like that's something that's talked a lot about these days, spirituality, all these things, unexplained phenomenon, whatever, plural, singular. So we we struggle with all these things. We as humans, and I think we as humans all understand, we recognize that the world we see, our day-to-day experience is one thing, but it's we just intuitively understand that it's that what is the what we experience is just a very minuscule fraction of the what is. I think we know that. We just know that intuitively. I think that when Einstein came around, started talking about, time is not necessarily what we think it is. Time, space can be contracted, can be bent, and all this stuff. I think humanity, we said, Albert, we've been thinking there's more to this story than we're seeing. Thank you. And I think that he did, the theory of relativity did open that door for us to really challenge our perspectives on reality. And to me, that's been a hugely powerful thing. It's allowed us to open up our minds and open up our imaginations. But also, on the flip side, because we took such hold of that as being the truth, it's also constrained us, because often when we're using our imaginations and so on, we have to say, well, that can't be right, because that would offend relativity, and we know relativity's right. So on the one hand, it caused humanity to open up its mind, collective mind, but on the other hand, it has constrained us. And I just find that very interesting, and that's just kind of, to some extent, is herd mentality. You've got outliers who are always going to be imaginative, and they're going to, think. They're going to think, I guess, unconventional thoughts and so on, and maybe they're not going to be constrained necessarily by the herd. And then there's going to be the herd who are going to believe, the conventional things that have, the wisdom that has become conventional by common usage. And they're going to herd everybody, and then there's going to be the outliers who will not be herded. And so I think this theory of relativity and how it has taken hold in our our collective consciousness and collective view of reality, I think that's a good example of just this herd, the way our human herd acts and reacts and evolves. So very interesting. So there you go. There's my first YouTube video. Hopefully you enjoyed it. Hopefully it provoked some thought for you. It's something that I've thought about a lot over time, and happy to share it with the world. Have a good day, everybody.